This video, we're going to look at the algebraic properties of our mod-in addition and multiplication. Our author puts them together in the following proposition, and I would encourage you to stop the video and copy the parts of this particular proposition down carefully in your notes, and then start the video and watch the rest of the video. So hopefully you've done that. Now, I don't want to actually read all of this stuff out loud to you, but I do want to kind of note that what the author is saying is that modular arithmetic works the same way ordinary arithmetic does, except for this very last property. In other words, addition and multiplication are commutative, they are associative, they both have identity elements, and the identities are named what we expect them to be named, and we have a distributive law that multiplication distributes over addition, and we have additive inverses. The only difference is multiplicative inverses. I am going to choose to only prove part of this theorem in this video. The author proves part 1 and part 6, and I am going to prove this part of the associative law. I will prove that there is an additive identity, and then we will prove that there are additive inverses. The remaining parts of this theorem are left as exercises for you to do. So let's get started on showing that addition mod in is associative. So show that plus mod in is associative. Now I want to actually remind you of the long way that we are writing things. If a and b are actually in the integers, then modular arithmetic is actually done on the equivalence classes, and I want to write the equivalence classes different than the integers, and that's why we're throwing in the square bracket notation. And in the previous video, we showed that if I want to add the equivalence class containing a to the equivalence class containing b, I can add a plus b and then find its equivalence class. Now I know that if a and b and c are integers, then I do know that a plus b added to c is exactly the same as a plus, put the parentheses around b and c. This is true inside the world of integers. Now let's look at what happens to the coset multiplication, or rather the coset addition. So I'm going to get started in this sort of a fashion. If we have the equivalence class containing a plus the equivalence class containing b, and I put that in parentheses, and I add the equivalence class containing c, I know this is going to be the equivalence class containing a plus b plus the equivalence class containing c, and this is by the definition of addition on the set of equivalence classes, in other words, inside Zn. And I know how to do this. This is going to be the equivalence class of a plus b plus c. And so this is also by the definition of addition on the set of equivalence classes. But it is important to realize that a plus b plus c is an integer. And so I know that in Z, the integer a plus b plus c is equal to the integer a plus b plus c. Consequently, I know that if I look at a plus b plus c and I want its equivalence class, it's going to be the same as the equivalence class of a plus b plus c. And I go from here to here because plus is associative on z itself. In other words, I am using this fact over here to justify this statement going from here to here. Well, once I have that, then it's easy. I just need a little bit more room. I can break this equivalence class addition up at this particular plus sign and write this as the equivalence class containing a plus the equivalence class containing the integer b plus c. This is the definition of addition on the set of equivalence classes, which is given the name Zn. And now it's just one more break this equivalence class up at that plus sign and rewrite this as the equivalence class containing A plus parenthesis the equivalence class containing B plus the equivalence class containing C. And at this point, we can now say that addition is associative on the set of equivalence classes modulo n, and that's what Zn represents. And so that means we've got the first thing that I'm wanting to prove in this video done. Let's look for an additive identity. Again, I'm going to use the full equivalence class notation. So I want to find an additive identity inside Zn. Well, what I want to notice is this. 0 is certainly an integer, so there is an equivalence class containing 0. And in fact, if you look at this, this turns out to be all of the multiples of n. And look at this. If I take any equivalence class and I add the equivalence class containing 0, by our addition definition, this is the equivalence class containing a plus 0, but a plus 0 is simply a. And I want to justify these. This equal sign is by the definition of addition on the set of equivalence classes modulo n, and this particular equality is because a plus 0 is equal to a inside the set of integers. So the equivalence class containing 0 is an additive identity for Zn. Well, the last thing that I want to prove is something about additive inverses. So now I want to find an additive inverse for the element, the equivalence class containing A, inside Zn. Let's see. The first thing that I can do is I can note this. A is certainly an integer, so minus A is also an integer. So there is an equivalence class for minus A inside Zn. And if we look at this, we see that this particular equivalence class here is going to be the additive inverse that we are looking for. So let's look at this. If I look at the equivalence class containing A, and I add to that the equivalence class containing minus A, that's going to be the equivalence class of A plus minus A, but that's going to be the equivalence class of 0. And I want to justify these statements carefully. This one here is the definition of plus inside the set of equivalence classes modulo n, This particular equal sign is because a plus minus a is equal to 0 inside the set of integers. But at any rate, what we've got is a, the equivalence class containing a, and the equivalence class containing minus a are additive inverses inside Zn, the set of equivalence classes modulo n. Now there's one last thing that I want to say about this particular additive inverse. There is a more natural way of writing it, particularly when we are doing stuff in the shorthand. So I want to make a note here. The equivalence class of minus a turns out to be the equivalence class of n minus a, and the reason why is pretty simple. Minus a is going to be equivalent to n minus a modulo n, since if I look at n minus a minus a, that's going to be n minus a plus a, and that's equal to n. So n divides n minus a minus a, and that will imply that n minus a and minus a are congruent modulo n. And this is useful because when we write Zn in the shorthand of just 0, 1, all the way up to n minus 1, then what we're going to want to do is we're going to want to write that minus 1 is going to be n minus 1, minus 2 is going to be n minus 2, minus 3 would be n minus 3. So in Z8, minus 1 is going to be the same as 7, minus 2 is going to be the same as 6, minus 3 is going to be the same as 5, and minus 4 is actually going to be itself. And that ends this video.